Here we're going to learn about EMF, electromotive force, the Nernst equation, and membrane potential. All right, how about EMF? Electromotive force, that's what EMF stands for, but that's a misnomer. In fact, EMF is not a force, it's a potential. Recall that the relationship between potential and force is minus the gradient of potential. EMF is actually a potential. We're going to show right now that the EMF, in fact, can be related to those electric potentials seen by the species that are oxidized and reduced in a redox reaction. Let's take the approach that Ball uses. He considers a reaction a general reaction where A and Bn plus. A is oxidized and B is reduced, so A transfers N electrons to B, and A is oxidized to An plus, and then B is reduced all the way down to B. The two half reactions for this are A is now being oxidized to An plus, and we're producing N electrons. Those N electrons are going on to B to reduce Bn plus to just B. So those are the two half reactions. We add those up, we get this whole reaction. Now let's let this reaction be at equilibrium. So at equilibrium, like we said in the previous lecture, that the sum for chemical reaction, the sum over all species of the signed stoichiometric coefficient of that species times now the electrochemical potential of that species, the sum over all those has to equal 0. And note that we have to have electrochemical potential because now we have charges, we have ions in our reaction. All right, now let's go ahead and do that. Let's do the products first, and all stoichiometric coefficients are 1 here, and the sign is positive for products and negative for reactants. So let's do the products first. This means that the electrochemical potential of An plus the electrochemical potential of B minus, okay, so we're just applying this, and this now we're subtracting off the products, minus the electrochemical potential of A minus the electrochemical potential of Bn plus. You add all those things up, you have to equal 0 at equilibrium. Let's go ahead and expand this out. The electrochemical potential of An plus will be the chemical potential of A due to concentration, plus there are N electrons being transferred here, N electrons being transferred, so the number of electrons is N times the Faraday times the chemical potential. This should be An plus of An plus, so we've expanded that out. Let's do the electrochemical potential of B, that's B plus. I claim this is 0. Why? Well, B doesn't have any charge, so Z is 0. There's no potential associated with that. So the electrochemical potential of B with no charge is just the chemical potential of B. Now let's do the reactants here. This would be the chemical potential of A minus 0 because A is not charged, minus the chemical potential of Bn plus, minus, again, N electrons are being transferred times the Faraday times the potential arising because you have Bn plus. All that has to equal 0. All right, so let's collect some terms. Just rearrange this equation. Do that on the next page. Let's collect the terms that don't have the potential in on one side. So this would be the chemical potential of An plus the chemical potential of B minus, and I'll write it this way for obvious reasons, or reasons will become obvious in just a minute, the chemical potential of A plus the chemical potential of Bn plus, and these are just chemical potentials due to concentrations of various species in solution. That's equal, I'll pull out the NF. This is the potential of Bn plus minus the potential of An plus. If you remember about how we defined the the free energy change of a reaction, this you just see, this is the reactants. Let me just go up here. An plus and B. An plus and B, those are the reactants. Here are the products, A and Bn plus, A and Bn plus, those are the reactants. So the products minus reactants chemical potential, this we defined as the free energy change for a chemical reaction. And that then is equal to NF times the potential B N plus minus the potential of A N plus. Now, what I'm going to say is that this represents an oxidation, a potential for oxidation. So, for example, if you have B being oxidized to Bn plus N electrons, this is the potential for that oxidation. This is the potential for An plus. This is, that minus that, but there's no electric potential here, so it's just that. And similarly that. So these are oxidation potentials. This is oxidation potential for B, and this is the oxidation potential for A, because of the way you've written it here. Now, when I was going to school and learning about chemical thermodynamics, back when dinosaurs roamed the earth, this is where you would stop. And in fact, what you would have are lists of standard oxidation potentials, and everything was determined in terms of oxidation. But what somebody decided, the chemistry police decided somewhere along the way, that we should no longer talk about oxidation. Everything should be written in terms of reduction. Okay, so now we talk about reduction potential. So oxidation potential, now if you flip this around, the potential will change sign. So this is minus NF. I'll write it this way, phi Bn plus minus phi An plus, where with that minus sign, now we're saying that these are reduction potentials. So that's somebody decided, I don't know, 20, 30 years ago that we should all talk about reduction potentials. So you don't stop here. We say, okay, these are no longer oxidation potentials. We're going to call these reduction potentials. Bn plus, how are you going to reduce that? Potential for reducing, potential for reducing. All right, so now if we look at this, compare it with what we had here. So we had Bn plus, okay, that's the reduction potential of what's actually being reduced, minus the reduction potential of what's being oxidized. Okay, so if you recall from the previous lecture, actually we can probably go up here in previous lecture here, when we reviewed equilibrium thermodynamics. Now if we go back up here and we review what were equilibrium thermodynamics, remember to calculate the cell voltage, it was reduction potential of the thing that was actually being reduced. In this case, it was copper, minus the reduction potential of the thing that was being oxidized. So it's a reverse reaction to subtract that. Well, that's exactly what we've done here. There's what's being in the reaction as written being reduced, and then you subtract off the reduction potential of the reverse reaction, the thing that was oxidized to be reduced. The thing is oxidized, now you have to go backwards to be reduced. So what we ended up with essentially is exactly what we had before when we reviewed introductory chemistry, but now we know that where these potentials come from. So just let me rewrite this a little more cleanly here. So delta G of the reaction is minus NF times the reduction potential of the thing that's actually being reduced as written in the chemical equation, minus the reduction potential of the thing that was being oxidized. This is called electromotive force, EMF. So that's what EMF is. And chemists give that the symbol E for cell voltage. Electromotive force is sort of a physics term. So this is an important equation. Let me just rewrite that again. Delta G reaction is minus NF times the cell voltage. So now everything we said about delta G of a reaction can be recast in terms of cell voltage. So cell voltage is just another way of measuring free energy changes, and there's a proportionality constant, a number of electrons transferred in the reaction times the Faraday. Let's just do some things here. Remember that delta G0 was equal to minus RT times the natural log of K. Well, oh look, we can just replace that with minus NF E0, we'll make that standard state, is minus RT times the natural log of K, or in other words, E0 is just equal to RT over NF times the natural log of K. Well, there we go. So E0, you measure standard cell voltage, talk about what standard cell voltage is in just a minute. It's just related to the equilibrium constant. So equilibrium constant is related to free energy, cell voltage is related to free energy. Everything is focused in a chemical reaction for chemists around Gibbs free energy changes. Oh, I don't know, want to do one more? Yeah, let's do one more. So we know that delta G for a reaction was delta G0 plus RT times the natural log of Q. Remember, Q is a reaction quotient. Oh, look at this. Minus NF E cell is minus NF E standard state plus RT times the natural log of Q. Or in other words, E cell is E0 plus RT. Sorry, that should be a minus. Don't forget. Let me correct that right now. Minus RT over NF times the natural log of Q. So there we go. A cell that not at equilibrium, not a standard state, you look at the Q, that will give you a certain cell voltage. Oh, that's kind of cool. So let me touch base with where we're going here. Okay, so what have we talked about? So we know what cell voltage is, and we know that we can do all these things. This is the important equation here. We showed that delta G is minus NFE, so E is another measure of G. Just to refresh our memories, it's an extensive variable. It depends on amount, but E is an intensive variable, doesn't depend on amount. Think about it this way. If you have, say, a AA battery and a AAA battery, and they're made out of the same chemical reaction, if you measure the cell voltage in both of those, it's the same. But the AA, it's bigger. You can get more delta G out of that. You get more free energy out of that simply because it's bigger. It depends on amount. It's an extensive variable. But the actual cell voltage as you measure doesn't depend on the size of the battery. So E is an intensive variable and G is an extensive variable. A few more words about this. Let's define, because what we're talking about in these equations here, let's say, look at this equation here, or let's look at this equation, let's look at this equation, there we go. What we're looking at here is half reactions. All right, so these are half reactions here. And so it would be cool if we can have different standard readings for these half reactions so that any reaction we can get by adding the two half reactions. We don't have to actually do it. So what you need in order to measure these half reaction cell voltage, so that we can use this here, the half reaction cell voltage is a standard state. So to make a electrochemical cell, you need both the reduction and oxidation for it to work. So what you do is you define for this half reaction, putting 2 electrons on H plus to make H2 gas, you define that to be equal to 0 when the reaction is at 25 degrees, 1 atmosphere H2, and 1 molar H plus. So these may be familiar to you from introductory chemistry. We use molar for standard state. We use atmosphere for standard state. So most people define the reduction potential for H plus to be 0. All right, here's our standard electrode page here. And let's see what we're looking for. 0. There it is. All these half reactions here are measured relative to this standard half reaction, where this is 1 molar is 25 degrees, H2 is 1 atmosphere. You set that equal to 0. Set that equal to 0. That's on one half of the cell. The other half of the cell, you just measure the potential relative to that, and that's where those numbers come from. All right, now just remember that other standard states are possible. For example, if you're into biochemistry, 1 molar concentration is really not a good standard state to use for living things because they don't like that high concentration of H+. So oftentimes, the biochemists use the pH equal to 7.4 or 7.0, meaning the H+ concentration is 10 to the minus 7.4 or 10 to the minus 7th. Again, like we said before, standard states, the number you get will depend on what your standard state is. And again, measure all reduction potentials relative to the hydrogen electrode. All right, so now we're getting places.